Welcome to Chemistry 101, Chapter 5, Selected Problems. What is the percent of calcium in limestone? Okay, so I feel like we've done this one before, so I won't spend too much time on this. I don't know if we did it last time, but you do the part over the whole times 100%, and it's asking for percent of calcium, which contains 9.88 grams of calcium. In limestone, the limestone is 24.7 grams. And then you just times that by 100%. So when I get my calculator out, I do 9.88 divided by 24.7 times 100. And I have 40.0% calcium. Okay, we are going to deal with chemical reactions and equations. You need to be able to balance. You always start with a balanced equation, and then we're going to use those mole to mole ratios for determining stoichiometry. So let's start balancing this. Okay, so are these balanced? Here we have carbon dioxide reacts with water to form carbonate. We have one carbon, we have 3 oxygens, and we have 2 hydrogens. So yes, it's balanced. We're supposed to decide whether this is a chemical reaction or a physical change. Because you have carbon dioxide, which is what you exhale in water, these rearrange. Notice they have the same, this is on your reactant side, and this is on your product side. And that's from that arrow here. These elements rearrange to form new compounds. And these new compounds have different physical properties. So carbonic acid here is your blood buffer. So that's your blood buffer. It's what keeps your blood at 7.2 pH, which is very different than water. So this is a chemical reaction. Now here we have the same substance. We have water and water on the reactant side and the product side, and we go from a solid, which is ice, to a liquid, water. So this is from a solid to a liquid. This is a phase change. And phase changes, they're still the same substance, H2O, H2O. So phase changes are physical changes. Okay, so it says write complete balanced equations for each of the following. Okay, so solid sodium hydride, and we put the parentheses S for solid, is added to water. We'll make that a liquid, L. Hydrogen gas is released, okay, so H2 gas. And this is when you're using these elements here, you got to think about your diatomics. So when they talk about hydrogen gas, hydrogen is one of the 7 diatomics. Released, and aqueous sodium hydroxide is formed. So here we actually use all of the parentheses, solid, liquid, gas, and aqueous. There's only 4 of those, so those are descriptions. Now you look and you see we have 1 sodium, 1 sodium. We have 3 hydrogens, 1, 2, 3. We have 1, 2, 3, because we're comparing the product side and the reactant side. And then we have 1 oxygen. So this is balanced. Okay, aluminum metal reacts with chlorine gas, that's one of the diatomics, to form solid aluminum chloride. And this is where you get your periodic table and you see aluminum is 3 plus and chloride is 1 minus. So then you do your subscripts where it's 3 aluminum and, my bad, there are 1 aluminum and 3 chlorides, and it's solid, so there we go. So these are combining aluminum and chlorine to make aluminum chloride. Now, is this balanced? No. We have, on our reactant side, we have 1 aluminum and 2 chlorine. On our product side, we have 1 aluminum and 3 chlorine. So what number can we multiply? And when you balance, you put the big number coefficients in front. So we're going to put these big numbers. You never touch the subscripts, because if you change the subscripts, you change the substance. So if we put a 2 here, now you can say 2 times 1 is 2 aluminum, because that's imaginary 1. And 2 times 3 is 6 chlorine, because you multiply those. Okay, so here, then we can put a 2 in front of aluminum. 2 times 1 is 2 aluminum. And then what number in front of chlorine would give us 6? A 3. 3 times 2 is 6. So now we have the same number of elements on the reactant side as we do the product side. And then we just check to make sure those are lowest terms. 2, 3, and 2 are lowest terms. Okay, we're going to practice more. We just did this one. So what we do here, we're going to have reactant side, and then we'll have product side. We take inventory. We say we have 1 aluminum, we have 2 chlorine. Here we have 1 aluminum, we have 3 chlorine, and then we're going to put the big coefficients in front. And we decided that if you put a 2 there, you have 2 aluminum. 2 times 3 is 6 chlorine. And then we have to put a 2 in front of here, 2 aluminum, and 3 times 2 is 6 chlorine. All right, so reactants, we have 1 lead. We have, now you want to keep the polyatomics together. So we're going to say we have 2 NO3, and we have 2 potassium, and we have 1 chromium chromate. Okay, so over here we have 1 lead, we have 1 chromate, we have 1 potassium, we have 1 nitrate. So now we got to think about the big coefficients that we can put in front of the substances to equal. We can just go through here. Lead is 1, so we don't have to worry about lead. 2 nitrate, we only have 1 nitrate. So if we put a 2 there, now we have 2 nitrates and 2 potassium. So now we have 2 nitrates, we have 1 lead, 2 nitrates, we have 2 potassiums, and we have 1 chromate. So this is balanced. And then you just check to make sure lowest terms, which is a 1, 1, 1, and a 2. All right, so let's go to the next one. Okay, so here we have, let's do our inventory. Lithium, 2 hydrogens, 1 oxygen. Here we have 1 lithium. We have, now we're going to keep the OH, well, because there's not OH on the reactant side, we'll separate it. We have 1 oxygen, we have 3 hydrogen, and 1 oxygen. Now, this one's a little bit harder because we have the hydrogen split. I like to go for even numbers. So if I put a 2 in front of here, then I have 2 lithium, and then I have 2 oxygens. Now I have 1, 2, 3, 4 hydrogens. Now here, I can put a 2 in front of there, and now I have 2 oxygens, I have 4 hydrogens, and then I would have to put a 2 to get 2 lithiums. So 2 lithiums, 2 lithiums, we always check it. 4 hydrogens, 1, 2, 3, 4, 4 hydrogens. We have 2 times 1 is 2 oxygens and 2 oxygens. All right, so let's go and take inventory. We have 6 hydrogens. We have our 6 carbons, 14 hydrogens. We have 2 oxygens. Over on the product side, we have 1 carbon. We have 2 hydrogens, and we have 1, 2, 3 oxygens. So that's our inventory. What can we do to get the carbons to equal? We could put a 6 in front of the carbon dioxide. Now we have 6 carbons, and now we have 12, 13 oxygens. The carbons are okay. Let's deal with the hydrogens. We have 14 hydrogens. We have 2 hydrogen. What number can we put in front of there? We could put a 7, correct? So that's 7 times 2. That's 14 hydrogens. Now how many oxygens do we have? 6 times 2 is 12 oxygens plus 7. 7, 8, 9, 29 oxygens. Okay, so we're good with carbon and hydrogens. Okay, now we have 2 oxygens and 29. I don't like the number 29. So what if we multiplied a 2 through? So if we multiply a 2 through here? We did 2, 2, 2 times, because I'm trying to get even numbers. 2 times 6 is 12, and this is one of those harder ones. 2 times 7 is 14. We can always reduce it later, but maybe this way we can deal with even numbers. So here we have 12 carbons, 28 hydrogens, and 4 oxygens. Here we have 12 carbons. We have 14 times 2 is 28 hydrogens. And then we have 12 times 2 is 24 oxygens plus 14 oxygens is 8 to 38 oxygens. 38 oxygens. Okay, so now we have 38 oxygens, and here we have 4 oxygens. So how could we get 38 here with 2? What's 38 divided by 2? 16. So now we can make this 16. We put a 16 oxygens there, and now 6 times 2, we have 38 oxygens. Okay, so now we have the same number, but our problem is these are not lowest terms, 2, 16, 12, and 14. So now we can divide everything by 2. So 2 divided by 2 is 1, so nothing there. 16 divided by 2 is 8, so you put an 8 there. 12 divided by 2 is 6, and 14 divided by 2 is 7. And some people will be able to just do this with odd numbers, but my brain just works better with even. So that's lowest terms. Write balanced equation that corresponds to the following word equation for a reaction in aqueous solution. Okay, so you got to go and look at your periodic table, and you would need to know that copper solid plus silver nitrate, silver is Ag plus 1, nitrate NO3, 1 minus, and that's aqueous. They say in an aqueous solution. Okay, and then copper 2 nitrate. So copper 2 nitrate is NO3, 1 minus. So if you do this here, you're going to have 2 nitrates. So we need parentheses. And then silver. And silver is a solid, because it's an element. All right, so we have 1 silver, 1 silver. We have 1 copper. We have 1 copper. We have 2 nitrates. So we got 2 nitrates here. So we have to put a big 2 there. Now we have 2 nitrates, and then we have 2 silver. So that would be a balanced equation. Okay, another goal for this chapter is to classify compounds. So you can read over these and kind of just look at different ones, but decomposition, combination, single displacement, double displacement, and combustion. So if you go to the previous one, anytime combustion is when you react something with oxygen gas and you always produce carbon dioxide and water. That's combustion. So you're going to react with oxygen. Double displacement would be if you have something that has an anion and a cation. You have to have an anion and a cation, anion and cation, they switch places. Single displacement would be what this is. So the copper is displacing the silver. So right here, silver on the reactant side is reacting with nitrate, but over on the product side, it's now copper that combines with nitrate and displaces the silver. So this one is a single displacement reaction. Decomposition usually involves carbon dioxide gas, or so you have a substance and then it decomposes on the product side. So if you have two elements in one compound, those are going to combine together. So that would be combination, because you got two elements and they combine together. So if you have like sodium plus chlorine, and they make sodium chloride. See how two elements have combined together to make one compound? So that's combination. Here we have one element and one compound. That's what we have here. We have one element, copper, and we have one compound, silver nitrate. And then the products, you have one element, silver, and one compound. So this is single displacement. If you have one compound, let's say sodium bicarbonate, and then you get, well, let's just make that bicarbonate, and now you have, well, two elements. We'll see some going forward, but this is basically one compound and two elements. That would be decomposition. So you can see that decomposition and combination are really opposites of each other. Okay, so here it says we need to balance the following equation and classify. So we can go ahead and classify. We have a compound and a compound, and the calcium exchanges with the sodium to combine with sulfate, and then sodium on the reactant side is with sulfate, but on the product side now it's with the chloride. So this would be double displacement. And then here's your reactant side, and here's your product side. And we have one calcium, we have two chlorine, we have two sodium, and we have one sulfate. And we're going to keep those polyatomic anions together. Here we have one calcium, we have, I like to keep them in order, we have one chlorine, we have one sodium, and we have one sulfate. So the sulfate and the calcium are okay, but we need to balance these. So if you put a 2 in front of the sodium chloride, now you have 2 chloride and 2 sodium, 2 chloride and 2 sodium. So that is how we balance that. All right, the next one. We have one element and one compound. And then we also now we have one compound and one element on the product side. The barium is being displaced by the hydrogen. So this is a single displacement. And we have one barium. We have one hydrogen and one chlorine. Here we have one barium. We have two, well, let's go to hydrogen next, 2 hydrogen and 2 chlorine. So if we put a 2 in front of the hydrochloric acid, now we have 2 hydrogen and 2 chlorine, and that would be balanced. All right, let's go to the next one. we have a compound and a compound, and then on the product side we have a new compound. Sodium is with the chromate, and over here sodium is with nitrate, and lead over on the reactant side is nitrate, and then on the product side is with chromate. So this is double displacement. And then if we want to balance this, we have 2 sodium, we have 1 chromate, we have 1 lead, we have 2 nitrates. And over here we have 1 lead, 1 chromate, 1 sodium, 1 nitrate. And so here we have 2 sodiums, so if we put a 2 here, now we have 2 sodium and 2 nitrate. So sodium's okay, lead's okay, 1 chromate, 2 nitrates, 2 nitrates. So it's balanced. The last one here is an element and a compound. So we have a compound with element, and then we have a new compound and an element. So this is single displacement. And you see that potassium is getting displaced, or the iodide is getting displaced by the chlorine. So here we have 1 K, 1 I, and 2 Cls. Here we have 1 K, 2 I's, and 1 Cl. So potassium's okay, iodide is not. Put a big 2 there, and now we have 2 potassium and 2 iodide. We're going to have to put a 2 in front of this one to get 2 potassium, and now we have 2 chlorine, and now you see that they all work out. Complete and balance the equation for each reaction below. Okay, so for this one you want to look at what type of reaction it is, and then you want to predict the products and then balance. So combination, calcium and nitrogen are combining to make a compound. So if you look at calcium on the periodic table, calcium forms a 2+ charge, nitrogen forms a 3- charge. And so if you figure out the subscripts when they combine together, that would be Ca3N2. And you could just put solid there. Most compounds are solid. Now we need to balance that. So we have 1 calcium and 2 nitrogen. And on the product side, we have 3 calcium and 2 nitrogen. So if we put a 3 in front of calcium, we have 3 calcium, we have 2 nitrogen and 2 nitrogen. So that is balanced. Okay, single displacement. We need to take zinc and displace the silver. So we have nitrate is 1-. You look at zinc on the periodic table and you see that it's a transition metal, so zinc can be a 1+, if that's what you want, and that would just be zinc nitrate, and that would be aqueous. And then we look and see they are balanced. 1 zinc, 1 zinc. Oh, we got to do silver metal. Silver, 1 silver, and nitrate. And so that's balanced. Okay, which of the following ionic compounds is expected to be soluble in water? Now, you need to kind of work on memorizing your solubility tables. I always have to refresh myself. Some of them I remember because I teach every semester. So look at your table 5.4, and when they're soluble, that means if you put them in water, they're going to dissolve. If they're insoluble, they will not dissolve. These are also precipitation reactions, so you're going to have to memorize what's soluble based on that. So anything in group 1, so these are the things I do memorize. Okay, so your group 1, your alkali metals, always soluble. So you can just write AQ. So potassium, sodium, lithium, and then there's polyatomic that's always soluble is ammonium. So these are your pluses. So these are the ones that are going to come first. Those are your cations. Now the anions that I memorized that are always soluble are like nitrate, and they're usually the 1 minus. And it looks like acetates are always soluble. So anytime you see these in a compound, you can just say, okay, that's going to be aqueous. Now, most of your sulfates are soluble, except when they're with, and I just do like Pa, like whatever, Pa. Just memorize Pa. That's lead, silver, and mercury. So anytime you get those, and also you can include barium, strontium, and calcium. Notice that these are your alkaline earth metals. So I think when you get more charges, you get stuff that becomes solid. So if they're insoluble, they're solid. Oxides and hydroxides are insoluble, except if you have them with the alkali metals. So this trumps. So anything in group 1 is going to be soluble. Okay, so here, what's the rule for halides? So Cl. What's the rule that you have to memorize for halides? Halides, most chlorides, bromides, and iodides are soluble. So most of them are soluble unless they're with 1, 2, 3, 4 cations. And what are those cations? These 3, lead, silver, mercury. Yeah, well, it's actually just 3 because it's mercury. It's just a different charge of mercury. So the Pa. So copper is not lead, copper is not silver, and copper is not mercury. So you're going to say that's soluble, AQ. Silver nitrate. Do you see that you have a nitrate? These are always soluble. You don't even have to think about it. Anytime you see nitrate, put AQ. Okay, we have a halide, chloride here, but it's with lead, so that's going to be a solid. All right, what about your hydroxides? What's the rule for hydroxides? Hydroxides, oxides, O2 minus, and hydroxides are insoluble. Okay, so that's a solid. Unless they're with the alkali metal, hydroxides, and then we have somewhat soluble are the barium, these here. So copper is not an alkali metal, so we're just going to go with insoluble. Write a balanced equation to describe any precipitation reactions that would occur. Precipitation reactions are, they go from aqueous, so they're dissolved, and then they become solid when they combine with certain cation-anion combinations. So K2 potassium carbonate, and they tell you right here that it's soluble, plus barium chloride, and that's somewhat soluble. And then we're going to do this do-si-do. So here you have, this is going to break down in 2 potassiums and 1 carbonate. This is going to break down into a barium and 2 chlorides. And then what's going to happen is they're going to displace. So potassium, which was with the carbonate, is now going to go with the chloride. And that's going to become, get your subscripts, KCl. So KCl, we have to figure out if that's going to be soluble or not. And then you have barium, and barium with chloride is now going to be with carbonate. So barium 2 plus and carbonate 2 minus. That's going to be barium carbonate. And now we have to apply our solubility rules to figure out if something's going to become an AQ or a solid on the products. So potassium is group 1, so that's always AQ. So we can write AQ there, AQ. And then barium carbonate. Well, let's look. What's carbonate? Most carbonates, phosphates, sulfites, and silicates are insoluble. And I do think about this when I see my 2 minuses. Like anything that's like 2 minuses, you got to know, hey, that could be a solid. Exceptions are alkali metals and ammonium. Well, barium is a 2 plus, and that's a 2 plus, so that's going to be a solid. And then you just want to make sure it's balanced. So obviously you have 2 potassium here, so you're going to need 2 potassiums here. That gives you 2 chlorines. You have 2 chlorines here, so that's good. You have 1 barium and you have 1 carbonate. So if you put the 2 in front of the potassium chloride, it becomes balanced. All right, let's do this next one. Lead, nitrate, AQ, plus potassium sulfate, AQ. Now, lead is going to be 2 plus here because nitrate is 1 minus, and there's 2 of them. There's 2 of them. And then potassium is a plus 1, and sulfate's 2 minus. So to predict these, I've got to now combine lead, which was with nitrate. I got to combine it with sulfate. So 2 plus and 2 minus, I can do PbSO4. I'm just going to put the parentheses there for now, and then I will go back and try to decide if it's soluble or not. Okay, the next one is potassium with nitrate. That's a plus 1 and a minus 1 potassium with nitrate. Now I know that's AQ because potassium and nitrate are both always soluble. Okay, so sulfates are like the carbonates. They're 2 minus. They're usually insoluble unless they're with group 1. Well, lead is not group 1, so this is going to be a solid. And the next thing I have to do is I need to balance these. So I'm looking at this equation here, and I want to make sure that it has the right coefficients. So we have 1 lead, 1 sulfate. We have 2 potassiums. So if I put a big 2 here, now I have 2 potassiums and 2 nitrates, and it is balanced. Distinguish between an electrolyte and a non-electrolyte. You will have to classify compounds as electrolyte and non-electrolytes. Electrolytes conduct electricity. Electricity when in water. So the way electricity conducts in water is if you break up things into like ions. So potassium nitrate in water will conduct electricity. In fact, your fingertips have ions in them, and that's how they work with the electronic screen to conduct electricity. So if something breaks up into its ions, that means it's aqueous. So if they're soluble in aqueous, then it's going to be an electrolyte. A non-electrolyte are your molecular compounds. So if you take sugar, sugar dissolves in water, C6H12O6, so it dissolves in water. It breaks up into like little sugar particles, but it doesn't break up into its ions. So there's no pluses and no minuses. And so there's no conduction of electricity. And so molecular compounds that do not break up into ions do not conduct electricity. So indicate whether each of the following substances is an electrolyte or a non-electrolyte. Well, this breaks up into its ions. Sodium hydroxide. It's soluble, that would be an electrolyte. H plus and Cl minus, these break up into their ions. So that would be an electrolyte. Your strong acids are strong electrolytes. Sucrose solution, carbon, hydrogen, and oxygens, these are all nonmetals. Nonmetals with nonmetals. These are molecular compounds. You have no charges. No charges, not electrolyte. Non-electrolyte. Okay, our last slide. Add the physical state for each substance in the following reactions. Then write balanced net ionic equations. All right, so here it's nice because they've already predicted our products. Okay, so sodium chloride, sodium is group 1, so that's going to be AQ. Silver sulfate, remember the sulfates are typically solids. Exception are sodium, potassium, and ammonia. So this is a solid. Sodium sulfate, sodiums are always AQ. And chlorides are typically AQ, soluble unless they're with Pa. And so A is silver. So that's a solid. And we want to balance. Oh, we got to write in that ionic equation. Okay. We're going to need some space for that. So, and you have to break these in their charges. 2 silver, well, but those don't break up. So I'm going to say you can't write in that ionic equation for that one because it needs to be AQ. So we'll do that when we can. I will go ahead and balance that though. You can do a 2 there and a 2 there. Okay. This one, copper hydroxide, AQ. Hydroxides are typically insoluble, but that should be a solid. So, because copper. So those are insoluble unless they're with like group 1. So that's solid. This is AQ. Chlorides, copper chlorides, that would be AQ. And then that would be actually a liquid. All right, so I think this one's going to be solid. No, because it's not a, remember the Pa. So this one is AQ. This would be solid. This would be solid. And this would be solid because there's the silver. Now, we can't really write a net ionic equation because you have to have aqueous. Aqueous goes to solid. Maybe we can for this one. Okay, so copper. Yeah, well, this won't be a double displacement. Copper, single displacement plus silver nitrate. AQ goes to copper nitrate, copper 2. So we're going to have 2 nitrates plus silver. That's a solid. That's AQ. And then you put 2 there and 2 there. And that would not be a net ionic equation. Maybe this one, iron 2 oxide, O2 minus, iron 2 plus, so that becomes FeO. And oxides are typically solid, unless they're with like group 1. Hydrochloric acid is AQ. This goes to iron chloride, which is going to be AQ plus water. So I can work some examples of writing net ionic equations, but these aren't your typical equations in which you would write a net ionic equation. So like I said, I just pulled these from the book, so we'll look at that in class. And that wraps up the selected problems for this chapter.